Thanks, Ethan. So I guess we're just about to start. Next presenter is Steve Brandt, I said on CactusThorn.py, new content for NRPy, and I'll let you do all the talk.
All right. So the inspiration here was, we've got CarpetX, which is really a nice tool. It brings us new capabilities in terms of GPU support and so on. But one of the things that I really wanted to see was the front end. And so you may be wondering what, I've got some business guy up on the screen here. This is the creator of Cactus. He left the field of numerical relativity because he had some bad experiences and decided he just couldn't get credit for the work he did. And he went to somewhere that would pay him a lot. He'd get credit that way. So that's the guy who, he worked with Joan Massot to create Cactus, but Paul was the major force behind it. Originally, before he created Cactus, he was working on something called the G code. What the G code was supposed to be was you just type in, mathematical expressions and you get a complete code out of it. And he eventually realized that that was just too ambitious, and he had to scale it back a bit, and that's where Cactus was born. But I think now with the kinds of tools that have come to be over the past, so he created it in 1996. So in the intervening years, some other tools have come into play which make it a little more possible to realize his original dream, I think. And that's kind of where I was seeking to go. I wanted to take the NRPy work that had been done by Zach's group and Cactus and CarpetX, and I wanted to bring it closer to that original vision. And we're not quite there, but I'll show you where we are. And so this is going to be somewhat informal. So I start, as we do with all things, with the wave equation. And I'm just going to be, rather than having a beautiful notebook for you, I'm going to show you just Python files, which are almost as good. So these notebooks are still not to where I want them. These Python files are still not to where I want them to be. I want to implement NRPy LaTeX. I want to bring that in here and do things with it. And we'll see how that goes. But here's the basic concept. So we have this thing called CactusThorn, and CactusThorn encapsulates the complete knowledge of what a CactusThorn looks like, including all the different CCL files and where they go, and what the makefile structure is, and how you create a makefile for Cactus and everything, right? And this thing was designed to use a Cactus driver, which we call either Carpet or CarpetX. Those are the two valid values to use for the ET driver.
So then, Steve, quick question. So CactusThorn would be applicable both for Cactus, for Carpet and CarpetX.
For Carpet and CarpetX, right?
Yeah.
Now there are some things that you can do with CarpetX that you just can't do with Carpet, such as declare centering of functions. But we can just ignore those and generate some code. So the idea was that we'll be able to work with both of those frameworks. And I'll show you more about that. Okay, so NRPy has this notion of parameters as well as grid functions. But what I wanted to do is I wanted to capture the parameter declarations so that I could use them all in my generated Thorn. So I have the Thorn objects. So when I declare the Thorn object, I declare the arrangement and the Thorn name. Okay, so this is the test one arrangement, Thorn wave NRPy, wave toy NRPy. Okay, so I'm going to declare.
Test one doesn't exist, will create.
It will create test one if it does not exist. Okay. There's a finite difference order parameter I declared, which I don't use. There's a wave speed, which I do use. There's an x naught, y naught, and z naught. So what I'm going to do with this wave equation is I'm going to create a Gaussian pulse and allow it to propagate through the grid. And so this is going to be the centering of that of that Gaussian pulse is going to be determined by x naught and y naught. And I think z naught is wrong because this is 2D and I should have deleted that. I think I just don't use it.
Steve, a quick question for you. Finite difference order. You have, I mean, the default is clear, but then you have Vmin and Vmax. So are you generating code that goes from second to eighth order, or
No, that's a declaration of a cactus parameter, and a cactus parameter requires that you specify a minimum and maximum value.
Okay.
I think the idea would be that the
But
thorn would
ignore,
support.
okay, so it will ignore those two and just generate the finite difference order, fourth order finite difference thresholds.
Right. Well, as I said, I don't actually use this particular parameter. It's just an example of a parameter I could declare. And what's going to happen is when it goes down to generate the cactus code, it's going to put that in param.ccl, and it's going to set the maximum value to 8 and the minimum value to 2, so that you'll have to specify your finite difference order in that range. If let me rephrase that. You'd have to specify the FD order parameter in your par file in that range.
Right. But you also have to generate the code to make it that. Okay.
Yeah, if you want it to be useful, you have to generate that code.
Yeah, gotcha. Yeah.
I have a question, quick one. If you want any value for a parameter, how would you do that?
I think you can put Vmax and Vmin, you leave them unspecified.
Okay.
Does it support strings? Like if you do a string with an asterisk, that's the normal cactus.
Yeah, no, if you put a none in there, if you just don't specify it, then it's going to be.
Oh, okay.
I think that's the way I have it working.
Okay.
I just feel better about actually specifying something personally.
Yeah. So it's just that if I look at this quite naively, I would assume that it automatically generates, whatever I need here.
Yeah.
in this
If you have no restrictions on your parameter, then it should be fine.
Okay.
But for this parameter in particular, I think you should specify min and max of 4, because it's going to be forced to find a different order before anyway. So.
Well, I could.
I mean,
Anyway,
it doesn't matter.
yeah.
So
This is just an example of how you can declare parameters, and they go through and get inserted in the param.ccl with the doc string that you specify there.
So this is an example of a parameter, just to quote a little bit of yesterday's conversation, that would be very hard to use if you don't actually write C code for it. Because how do you teach Python that that's a parameter that you're going to have to do a bunch of if statements to call different functions and compute finite differences a different order?
Well, you have to generate all those different orders, and then you have to.
Yeah, but you're still going to have to write one C function by hand.
Okay.
Right.
Okay.
Well.
But yeah.
Okay. So.
Yeah.
So then what we do is we go through and we generate some grid functions. So we're going to generate UU RHS and VV RHS and UU and VV in the NRPy way, and this is specifying that UU and VV are the main ones that we're going to evolve, and we're going to also need these right-hand sides. Now, this CactusThorn understands that if you put an underscore RHS, that needs to be that's something that either MAL or ODESolver needs to know about, right? And it will specify it in the correct way for either of those packages, depending on whether you've chosen Carpet or CarpetX as your driver. So this is just going to use that simple naming convention to identify right-hand sides. On line 28, I have.
Are you forced to do it that way? Is there another way you can do it?
No, you're forced to do it that way. That's the convention I just stuck with.
Okay.
I mean, if somebody decides that's not the right convention, we can come up with something else. But that's I figured that seems to be like the easiest thing,
yes,
right? It's kind of like the underscore D or underscore D hat conventions, right? So it sort of fits in with the NRPy philosophy in a way. There is a possibility for creating temporary variables that only has meaning for CarpetX, and there are two types of temporary variables that you can declare. There is a tile temp and a scalar temp. And a tile temp only gets allocation for a single tile. So when you're running on the CPU with CarpetX, it will divide your computational domain into tiles for purposes of cache optimization or whatever. And it will do computations on one tile at a time. And This allows you to create temporary variables that you can calculate on a whole tile. And derivatives are an example of something that you do this with. There's also a scalar temp, which is just a single double precision value. And the use there is kind of like it's just a way to break up your expressions. Now, NRPy has a built-in functionality, common expression elimination, that you can use. But the problem with that is, if you get into, when we got to our Z4C example, that wound up getting into a situation where it was taking hours to generate the code, and it was just unusable. So we needed to do some manual breaking of the expression. And this allows you to do, and the scalar temp allows you to do that. The next line we have XYZ, and this is another thing that is highly dependent on Carpet and CarpetX. So if you're in Carpet, X, Y, and Z are grid functions, which have their values filled in for you and that you can just use. In CarpetX, that kind of doesn't make sense anymore because you now have centerings. You can be vertex centered or cell centered, and that's for each dimension. So you would potentially have 8 different grid functions for the different centerings, and it just becomes a little unwieldy. And so in the CarpetX framework, these are no longer grid functions. They're members of a point desk operator that is available inside loops. So what we just needed was some kind of different way of handling those things in those two frameworks that looks the same to somebody who's writing NRPy. So we have get XYZ, and it'll just do the appropriate thing.
Just a quick question here, maybe more on the Carpet framework together with multi-patch. Is that something that you can call here as well? So do you have?
I have not even considered doing anything with multi-patch at the moment.
Mm-hmm.
I mean, obviously that needs to be done,
Mm-hmm.
but this is the wave equation.
I know. Yeah.
So this is a work in progress, right?
Mm-hmm. No, of course, yeah. I'm just asking, what you already have, and
That's not attempted yet. Okay, so here I'm using some of the NRPy framework for setting a finite difference order, and I am declaring a rank 2 derivative tensor with sim01. And then I have 2 different formulations of the wave equations themselves. Now this is the one without using temporaries, and this is the one using temporaries. Now NRPy has this data structure called LHRH, which allows you to specify a left hand and a right hand side for an equation. And there's really no need for these temporaries. I mean, it's a tile temp, and it's one of the things it's used for, but the same functionality is present here. It will work just as well. There's maybe slightly different optimization properties. So UUDD is going to be delta x squared, and UUDD11 is going to be delta y squared. This marker loop here is going to, so normally what's going to happen when you have this array of equations is it's going to split, it's going to generate a single loop which will do all the expressions. This little delimiter here, this loop thing, is going to cause it to create 2 identical loops, one after the other. Sometimes you have to break up the loops to save the instruction cache or whatever reason. And so that just gives you a way to do that. In some ways I don't like that, because what I want this, it gets the impurity of optimization into my specification of the problem. But in some cases it's necessary. So the capability is there. Okay, so you specify sets of equations as an array, and these are the evolution equations. Then I specify initial value equations, and the way I've done this, the right-hand side for VV is going to be just 0, but I can't put a 0 there because that will confuse SymPy. So I have to do a simplified version of 0. On the next line, I have my pulse, which I said it was Gaussian. It isn't exactly Gaussian. It's got a trig function because I wanted it to be something that matched my periodic boundary conditions better. But you can put an arbitrary function there, and because I have the parameter x0 and y0, I have I have the possibly, the coordinate values, whatever they are. I have this simple k, which I defined as simplify pi over 20. And so I can specify initial data in that format, and it will work. Okay. And then I start creating the functions. So I have the initial value, the wave init function, which takes the init equations. It operates everywhere. So if you're familiar with programming Cactus, you know that we have this concept called presync, where in the schedule we declare whether something reads or writes, and whether it reads or writes the interior, or so on. And this is a where specifier. This is saying that we want to compute everywhere. I think it will figure that out on its own if you don't specify it. And the way it does it is everywhere is the default, and if you're taking a derivative, then it's interior.
One more question here, because I see that you're also setting the schedule bin as initial.
Yes.
Do you still have this functionality that you can specify to schedule it, say, in initial, but before function X or after function Y?
Yes.
As
This
you have
is a
mentioned.
string that just gets, this is a raw string that just gets inserted into the schedule.
Okay, okay. So you can
so-
put in the standard form, well, the
Right.
kind of cactus form that you
Right. So just don't put Johnny drop tables there or whatever. Everybody knows that comic, right? Johnny drop tables. Okay, we have to take a deep one. Hi, this is your son's school. We're having some computer trouble. Oh dear, did he break something? In a way. Did you really name your son Robert Drop Table Students? Oh yes, little Bobby Tables, we call him. Well, we've just lost this year's student records. I hope you're happy. And I hope you've learned to sanitize your inputs. Your database inputs. Okay. So, so I don't sanitize that input, is my point there. All right, and they all have to have a doc string, and then there's a centering that you can specify for the loops, for the function that you're creating. And that centering has to match with the variables that you're assigning. So you can't, loop over VVV and assign something to CCC. There's a check for that. You can read from VVV, but you can't assign to VVV if you're centering to CCC. So that's the correctness check that we have there. And so I have just two things that I'm specifying here. I'm specifying the evolution and the init. Now I have a special magic here for the schedule bin. It says RHS. And we have a different schedule bin that you're going to want to use for the right-hand side of an evolution equation, depending on whether you're in Carpet and CarpetX. So if it sees RHS like that, it's going to replace it with the appropriate thing. And so I set this up with environment variables so that, multiple people can run the same exact Python file and just point it at their own Cactus installations. It just makes it a little easier. So this is where you're installing. This is where your Cactus home is. This is what the name of your config is, and then this is where your Thorn list file is saved. And then you just call generate with Cactus home, Cactus config, Cactus Thorn list, and it will go to your Cactus installation, and it will insert everything that needs to go there. If we look at,
wait a second here.
Yes.
When you say generate, does it mean it's also going to compile?
That's what I was.
It is not going to compile. It's going to generate the source code.
But why do you need the Thorn list then? Or does it generate the Thorn list?
Because
for
the
you?
Thorn list needs to have test one NRPy toy, NRPy wave toy in it. It's got to have, your Thorn list has to have this in it.
That's right, and the.
And it's going to insert it into the thorn list for you.
Okay, so that's it for me, but I still shouldn't need the config file just yet, right? If I only generate the code and not compiling the code, then I shouldn't need yet the configuration script.
Well, you need the config. The reason you need the config is because there is a thorn list in the config, and so if you've got a config that's built there, right, it won't build your new thorn unless you add the thorn to that thorn list. So config sim thorn list, it's just one wave toy NRPy added to it. That's why it's there.
But those are mandatory? You have to provide those, otherwise you will error out.
I don't think so, but I mean, if you don't do that, then when you go to build the thing, it won't build, and you have to say, oh yeah, I forgot to add that. Right, so it just adds it for you.
Yeah, but say I just want to generate the code and look at the source code before I even attempt to build the program.
Yeah, I think you can leave those out. It should be fine.
Because, I mean, it would be good, for example, I don't know what it does, right, but at the very least, there needs to be enough intelligence in these things so that it doesn't add the thorn if it's already in there.
Yes.
And then if there's the intelligence, I always feel, oh, I'm adding intelligence, probably going to be quite intelligent enough.
That's all it does is check to see if it's there, and if it's not there, it adds it.
Does it know about problems?
Yeah, so it knows about comments because it's looking to see that the thorn name starts at the start of the line. So if there's a pound there, then.
But do you get an error message if you already have a thorn with that same name?
No, it just does nothing.
But then you're creating
It's just
a thorn.
yes, no. Look, yes,
Yeah.
you could cause a problem for yourself, but how does it know the difference between a different thorn that you created with the same name or a modified version of this thorn?
It is a warning. It says I already
Yeah.
found
Yes,
it.
it does
sure
say,
that they don't
what it does, when you generate it, it says Thorn is already present in Thorn.
Oh,
Okay, so you do have an
There
error
is
or
a
warning
warning, yes.
message.
It's not really a warning, it's just
An
saying that,
information.
yeah.
Also, like it's irrelevant, but those checks that you check for the environment, those should happen at the very top, because then you don't do all of this.
Yeah,
Yeah.
sure,
If there's an error. right?
sure, but
Yeah.
we're talking about
Yeah.
a minute to run this
Yeah,
at most.
but if you
right?
do it for Z4C and you
If
wait
you do
1
it for
hour,
Z4C,
and then it says,
sure.
oh, I couldn't find the path. And
Right. Okay, so let's take a look at the pre-baked cakes. So I have my two scripts that I use to run this. So there's carpet.sh, which I just sort of set my various variables. I call the wave toy, I run it, I post-process the output, generate an image. And this one still has a problem with the boundary conditions, which I haven't worked out completely, but nothing's perfect. And then we can look at the code that it generated. So there's all those things. There's the parameter CCL file.
I have a question.
Yes.
So in your Python file, you didn't specify the types, but how do you get the types here? The CTK.
Well, because so if you pass it integer values, if everything's an integer, then it assumes you want an integer type. And if you put anything that's a real value, it assumes you want a real type. So it's just looking at the type of the Python objects.
Okay, but in Python, sometimes it's ambiguous.
There is also, I think I also have bool, yeah. I don't know that I did, I don't remember if I implemented that or not.
And then every parameter normally you have to specify the type of parameter by hand.
Right, but I figured it out in passive.
So I've seen thorns where people specify reals as in.
Yes, you can do it, right? But and if people don't like that I do it this way, that I can change it, it's fine. But if you really want to, if you really want the thing to be a real, you just make one of those numbers, the default or the minimum or the maximum, you make one of those a real number and it'll be a real.
But the user wouldn't know that before you would do it, then you get an error, and then you would see, oh, there's the wrong time.
Yeah, well, I mean, in any
Like
package,
if you just do a real, you want a real, but you do min 0, max 1.
right?
Right?
So
Then it would error out at the end, like the code would behave weird because it's assuming that that parameter is an int.
So
you actually
everybody has
expected it was a real.
everybody has different notions of what's intuitive behavior. And
Right, I guess.
and this is my notion. And as I said, if people want something different, I'm perfectly happy to change it.
For the wave speed, it's 0.1 is the minimum, but the maximum is 100. It's not 100.0.
Right.
And so if you wanted 0 and 100, that would be declared as an int.
Unless you
that's
put
nice.
0.0 or 100.0.
It doesn't look, if it parses as a thing, it looks, if it's the Python type integer. Python has type too. If you
Right,
pass
but-
one
but if you-
Python, it's
But he would, no,
If
If you
did
put, if you
zero,
put 0 and 100, it would require integers.
you would assume it's integer.
Right, but if you wanted that to be a real,
But if
just
you put 0.0 and 100, then
Right,
it would,
but the user
As
wouldn't
user-
know that, that's my point.
Yeah.
If you're
Well,
writing
that's-
the code
so-
for
so-
the first time,
yeah.
you would
Well-
put 0 and 100, this would be generated as an int,
Yeah.
and when you run the Thorn, there would be an
So-
error.
In that
I
respect,
don't-
you shall read the documentation, which
Yeah.
hopefully says what it's doing.
Or
You can't
specified
use-
by
Yeah.
look, you can't use any software without reading some documentation, and so this is the question of what's most intuitive. And again, I made certain decisions based on what I thought was most intuitive, and if it turns out not to be the case, if people get confused by the way something behaves, it's perfectly fine, I can change it. Or I can add a parameter that allows you to specify the type, whichever.
That's maybe the most reasonable, because I would do exactly this error the first time and then go and search in the documentation
Yeah.
why,
I mean, at the end of the day, you are writing code for the Einstein Toolkit.
Yeah, at the end of the day, you're writing code for the Einstein Toolkit, and you've got to understand at some level what you're doing.
Yeah, I mean,
But in any event,
yeah. I mean, you can even make the type optional, I guess. But,
yeah, I could do that. It's not. My feeling is generally I want to have the minimum amount of clutter I can avoid, right? I want to minimize the clutter, and that was an effort to minimize clutter. So, but I'm perfectly fine with changing that if that's what people want. Here's my interface definition.
Steve, yeah, can I ask a quick question?
Absolutely.
Yeah, so one of the relatively new features in NRPy regarding registering grid functions is the requirement to scan its value at infinity, which is very useful, of course, in BSSN. In fact, these are required in.
You're breaking up, Zach.
For new red. And I'm sorry. Can you hear me better now?
Yeah, it's just you just sort of dropped out there mid-sentence, and you said something about specifying value infinity, and then you dropped out.
Yeah, so specifying the value at infinity of any grid function is required for registering grid functions, as well as the wave speed of a given grid function. These are inputs, of course, into NewRad, which Terence Pierre Jacques reproduced a version of that for NRPy. But what I'm thinking is you could use this, and then that way you could use these inputs and then couple this wave toy to NewRad. Just a thought.
So Zach, how are you doing it? Would that be then written into the param.ccl? Because I'm thinking, what if you wanted to use something else than NewRad, but you have already these values specified?
Healthy, not parameters, grid functions.
So, but if you, in your grid functions, if you define the asymptotic value and the wave speed, at the moment it's a parameter that you define in the param.ccl. So is that where it will be put, or will that be part of the grid function?
No, as I recall, yeah, this is input. Yeah, so I think there's a NewRad function call where you actually use those values. Right. So yes, I guess in principle you could just specify them in param.ccl, and if your PDE had a different character, right, then the wave speed would be different. Or I guess you could specify the wave speed as well.
Or let me put it this way: at the moment, at least, the way we have it is that we define those parameters in the param.ccl and then put that in when we call the NewRad boundary conditions. Gotcha.
So I guess at the very least, registering your grid function with we call it f infinity, the value of the grid function in infinity, and the wave speed would.
Okay, so you're breaking up, I think, again.
Zach,
can you
are you still there?
Can you still hear us?
Sorry, am I cutting in and out? Let
Yeah.
me move
Yeah,
to my
unfortunately.
cellular connection, sorry.
Yeah, so there's just one thing that why I brought this up. So imagine you don't want to couple to new rad, but you want to use some periodic boundary conditions. But now you're basically defining things that you need for radiative boundary conditions in the definition of your grid function.
But you can make those optional.
Oh, you can make stuff.
Yeah, and then
Okay.
you can make them optional to none, and then if it's none, it will not add it.
Okay, okay.
So that also kind of answers my question, because when Zach said, oh, we are now requiring that you give us parameters for NeuRAD, and then I would object.
Exactly.
Because not everything uses NeuRAD, none of the hydro variables do.
No, right. I think it's just that, like, it would be nice to have that, the ability to request those types of boundary.
Yeah,
conditions.
Okay, but it's flexible, so it's optional.
No, not mandatory.
Okay. Yeah, this is
Whenever
why I
you
was
add-
maybe.
Yeah.
Okay,
I mean, even in this example, right, you want to do periodic boundary conditions, wouldn't make any sense to
That's right,
specify
yeah.
new
So you want to be
parameters,
able
yeah.
to optionally put that in,
Yes,
but
yes,
then
exactly. Yeah, you
it's not
just-
mandatory,
in
so you
that
can
place
actually
where
couple
you-
to different
Yes,
boundary conditions.
exactly.
So on,
Yeah.
And in fact, I mean, I've been using NRPy, and it has not required me to do it. Maybe Zach it's sort of he's thinking of it as a requirement, but it's certainly nothing that NRPy enforces at the moment. And I've been keeping my repo synced with the master.
But it will be if you specify the boundary conditions to do radiation. But then it would not belong in the Einstein Toolkit, it would be a standalone NRPy code.
Yeah, and I don't do that, so.
In that case, it would force you to specify when you request the boundary condition to be radiation. You have to pass the value of the grid function at infinity.
Right.
Yeah, and I mean, NeuRAD does need those
Exactly, yeah.
parameters. that's
But
right.
you already have something like that in the toolkit, and so then you would be at the moment of grid function declaration, you could in principle specify.
Okay, and then here is the schedule. So you notice it creates the storage declarations, it creates a register function for vol, and then it also specifies the reads and writes of things. So this one is going to write to the interior because it's doing derivatives.
Quick question
Yes.
here. For the right-hand side, you should only need one time level, right? So the ones that need 3 time levels are the grid functions themselves.
So this has to do with different requirements of Carpet versus CarpetX.
Okay.
And so for these in Carpet we need 3. In the CarpetX, those are all going to those storage declarations are all going to be 1.
So in Carpet for the right-hand side, you only need 1.
If you're going to evolve it with mol, you need to have 3, is what I was told.
No. The function itself, you need 3, but the right-hand side, you only need 1.
Oh, for the right hand side,
Yeah. So and that's why I'm asking. So it says.
I just put 3 on everything for Carpet and.
Gotcha. Yeah, because I usually try to think about this more carefully so that we don't have to store too many variables.
Right. No, and I should probably change that. I just
Okay, gotcha.
So the Carpet end of this generation has received less attention than the CarpetX one for obvious reasons. I do want them both to work though.
Yeah. No, that's fine. And it's not that it wouldn't work. It's just
right. It's just wastes storage. And then we have the source code. So we've got the register function, right? And we've got wave init, right? So this is going to generate the functions with the cosines and so on.
I think the behavior with the new rad would be similar to the register MOL stuff, right? If you specify that, then there should be a function that already says the new rad what is the boundary.
I'm not familiar with the new rad stuff, so.
Yeah, but it's something that we could definitely add.
Sure.
Yeah.
Okay, the other thing that I have done in the course of doing this generation is I have brought in Clang format. So all the code that gets generated, all the C++ code that gets generated has been run through the Clang formatter, which is the same standard that Cactus itself uses these days. All right, so that's the Carpet version. So let's look at the CarpetX. So I've got a CarpetX script, which is a little longer, and that's probably mostly because I've been working on it longer. This is the one that's using the singularity image to compile, and I've got that in my Cactus Home project as Brandt Cactus Amrex Cactus. So if I go into that one, Oh, you know what? All right, let's just run it. Yeah, it's not there because I regenerated my cactus last night and my CarpetX installation last night. So what this script is going to do is first it writes out the files. Now, one of the things that you notice is it tells you what files it's writing. What it does when it goes to generate those files is it checks to see if the file already exists, and if the file already exists, it checks to see what the contents are. If the contents are unchanged, then it doesn't print out a write message and it doesn't write the file. Only if it actually writes something does it print that write message. There's an option that you can give it to tell it to print a diff of the two files before it replaces it. So if you're wanting to see what's changing, you can look at that. Okay. So this is recompiling everything. And what it's going to do after it finishes compiling is it will run the code, and then it will run a Python script to read the OpenPMD output files and generate still images, which I can then use FFmpeg to generate a movie. And yeah, as you can see, it compiles.
This version of the CactusThorn already has the UA and L.
No, it doesn't have. I haven't put that into anything yet.
So no Einstein notation of that.
No automatic Einstein notation yet. I wanted to, before I started working on that in any kind of serious way, I wanted to look at NRPy LaTeX and maybe use that as the way of doing it. But we'll see. I think it looks to me like NRPy LaTeX can do what I want for that, so I'm going to try that first.
It would seem complementary to me.
They could be.
That this is, if I want to enter the Python code, work on the lower level, I would use the answer notation there. And of course, if I come in from an equation, then I use NRPy LaTeX, and then it has its own summation. Which
Right.
means, of course, because LaTeX has to just.
Right. And it may be complementary, and I may want both, but I just wanted to see NRPy LaTeX before I invested too much time and effort into something. So this time I got a permission denied from writing a file. Whatever. Let's look at the generated code. That's what I mostly wanted to see. So once again, we've got parameter CCL, which I think is the same. We've got interface CCL, which is different, right? We've got these different tags. We've got the centering in here. And we have the RHS declaration, which CarpetX uses instead of the null register mechanism. It's got the different header files that it needs to bring in. It's got, requires arith and loop in the configuration, and it's got a schedule, right? With
ODESolvers instead of MOL.
Right, with ODESolvers instead of MOL, and storage of size 1 for everything. All right, in the source code, we've got a bit more boilerplate. We've also got checks to make sure that there's the correct number of ghost zones. I could probably optimize out the check when it's 0, but it currently prints it anyway. This is all the various pieces of code that get generated for the map, for the loop. Here's the this is something Eric inserted on me, which I don't remember seeing before. This pool effect thing. That's the loop. So he changed the loop, the way the loops look on me. But in any event, here we go with the code for V and U with the cosine and everything, using the different ways of expressing X and Y variables. Okay? And again, it's all formatted with blank format. Now, this is great for the wave equation, I think, that we can specify fairly simply, right? We just specify a few parameters, say we want these grid functions, and here's how they're evolved. What about Z4C? Now, Z4C is also a work in progress because it's far more complicated right now than I want it to be, but it's still less complicated than it might be. So in this case, we're going to make use of this ability to set a precision type in NRPy. So you could, by default, this is just double, but you can specify it to be a CCTK built-in type if you want to. And here we have it specified as real vec. And the finite difference order is specified. And there's this function flatten, which is going to take a list of lists of lists, or however many you have, and turn it into one flat list. There's some summation functions which really should go away, right? And tensor functions that really should go away. I'm hoping to use NRPy LaTeX or other mechanisms to do that. One of the things we have to do is we have to import GXX, GXY, and so on from the ADM base, and that breaks the NRPy convention for how variables are declared. So I made an extension here that allows us to get the other kinds of names. So when I declare the GDD variable, for example, here on line 107, I specify this name function, and this will declare it with the convention that I want. So NRPy can just go ahead and do all the things it wants to do, but it just, instead of it being called metric or GDD00, it will be called GXX. And as near as I can tell, that doesn't break anything, and that different naming only comes about if I specify that name function when I register the grid functions. Something else that's new in this Thorn relative to NRPy is this register grid functions for single rank n. So NRPy had the ability to declare rank 1 and rank 2 when you had this, as part of the name, and it didn't have a function for 3. And I was starting to write one for 3, and I thought, you know what? Why not one for rank n? And just use that. And then if I want 4, I've got 4, and if I want 5, I've got 5, or whatever. So that's what I did, and that turned out to be useful. Because what happens is when you declare a grid function this way with a rank 2, it's going to, and symmetry 0, 1, you're going to have 6 variables, and they're all going to go inside the same Cactus interface group. So you'll have a single group named metric, and then inside it you'll have GXX. And then you have a single group. This is going to be an external Thorn, so it's going to say there's a single group ADM in the ADM Thorn with names GXX, GXY, and so on. And it understands that that's the way it's declared there. If I was declaring my own function, not doing something from ADM base, like I do with, say, go down a ways. Yeah. So yeah, so you go down with like this K hat or this A tilde DD, right? If you do the A tilde DT, all those things will be in the same group. And there's just lots and lots of things declared here. And this can be made more compact and made to look nicer. And this is, I'm hoping I can leverage I can leverage NRPy LaTeX to make this look a little nicer.
So maybe you can, because some of the tensors share the similar property, which means centering is the same, then you can make a list which contain all these tensors. And
yes.
You can go over.
Yes, absolutely.
Although, wait a second, because, well, I don't know how it works in CarpetX. In Carpet, if you use an MOL, you have this relation between what is your right-hand side and group and what is your actual grid function group, right? So, and that's why I think things, for example, like the metric and the extrinsic curvature, or the traceable part of the extrinsic curvature are typically 2 groups. I don't know if that's still needed here, or if you can have that in the same group as Levi suggests.
So at the moment, the only way the groups get generated is with this rank n, and everything generated from that is in the same group, and that's the only thing it does. I mean, again, you know, this is a work in progress, and this is a starting point. And you know, I learned many things I had to do from the wave equation, and many more things from trying to get this Z4C in some basic working order. And I assume that, you know, for the first 10 applications that you do with something like this, you're going to discover new things that you need to do, and new wrinkles on you know, where your assumptions break. So then we declare the derivatives and more temporary functions, and then finally we start on expressions. We have this initial expression, which you know, has got some of these ugly little loops written in here, which need to go away. And we did find, you know, in our first version of creating the Z4C function, we did wind up with one error where, you know, the wrong loop index was put in the range there. And you can see how easy such a typo is to make, right? You shouldn't have to specify all these loops by hand. It should just know what to do. And that will be the next iteration of this, is we'll figure out a way to make that automatic. And so you put all that together, you add it, you put the next one together, and you add it. And this is able to figure some things out, right? So one of the things it figures out is with temporary variables. If you have a temporary variable, you have to assign it before you use it. If you attempt to use it first, you'll get a code generation error, right? And it will tell you what variable you did, what function, and so on. And when you get to the end of the day, you get something far more complicated that gets generated. Oh shoot, what was the arrangement name? I forgot already. CarpetX and NRPy. Okay. So we have a bunch of different things in here. So we have Z4C, RHS, which is the most difficult one to get right. And now we're seeing some rather substantial amounts of code generation, right? So it goes on for a while, as you can see, with all the stuff that it generates. Where's the end? There we go. 7,000 lines of code.
How long does it take to generate this one?
Well, let's run it. So before I run it, let's not do the whole workflow. Let's just make sure we just run the generation.
Hey, Steve, quick question.
Yes.
Can you hear me? Okay, great. Did you have any problems getting it to compile expeditiously?
Yeah.
Or were there hangs?
So you probably missed out on this part of what I was saying, but the problem that we had, the common sub-expression elimination for some of these expressions wound up to the, you know, going into the hours of code generation. We didn't actually ever wait for it to finish.
Yeah.
This is why we introduced the scalar temp variable type. So this is kind of like a manual CSE that cuts down on the work the CSE processor needs to do. So in this case, it was able to generate the Z4C in 27 seconds.
Yeah, it's interesting and a little bit confusing because I think BSSN, as it's coded in NRPy, doesn't take that long to break down. Now, it does. There are some secret tricks that we use. Maybe not so secret because it's open source, but we do define the Ricci tensor, the 3 Ricci, as its own set of grid functions, 6 grid functions. And we found that I think that has 2 effects. First, it greatly reduces the amount of time needed for code gen. Second, it also provides a nice performance boost in the underlying C code. I mean, it's not huge, maybe 5%, but I'll take it. So that's just one idea. I mean, I think if you define Ricci separately, I think it'll fix all your problems, I'm guessing.
I have a question with that. So you said you define the Ricci tensor as a temporary variable, right? So which means
no, I define it as a grid function, a 6-grid function.
Okay. But in some sense, you did something which can do better compared to the CSE, because you said you benefit a lot by doing that.
This is not related to the number of floating point operations that CSE is able to reduce things to. This has to do with the fact that the typical CPU just can't handle expressions that are that large. I mean, I think if you split off the Ricci tensor and you count up the number of flops, it is actually more flops than if you were to reuse the sub-expressions in Ricci that are common and shared among other tensors in Einstein's equation, in BSSN at least. So this is not really a fault of the CSE. It's more of a fault of modern CPUs not being able to. And I know Eric knows a lot more about this than me, but we've all found, MLBSSN, for example, splits BSSN equations into 2 parts. That is kind of how we do it in a sense. We split it off into, you compute Ricci first, and then you compute everything else. I found it really high finite difference order, in fact, that if you split off, again, some of the other right-hand sides into another step or sub-step, you can get a little bit more performance boost. And again, that has completely to do with the fact that the CPUs, they have to read in so much data from memory in order to compute some of these expressions in BSSN. If you reduce that, at the end of the day, what I find is that it's the memory reads and the memory writes. Primarily, I guess the memory reads from non-local parts of memory. That actually it may be the most significant contributor to the performance.
Right. So what happened? The way this came about, right, is I had the wave toy working, and Eric said I want to try entering the Z4C equations, and part of the purpose is to just stress the generator. And when that was done, this is the problem that we hit. Now I'm sure there's 100 different ways of splitting things up, and Eric chose to do things the way he did for whatever reasons. But as I said, the first pass, it was the last set of equations. It just the CSE splitter just got overworked. I guess it probably scales like n squared or something, and the n got too big. But
no, it's actually a beautifully it's a beautiful recursive algorithm. That I think the issue might have been that it was a generation of the expression that was taking all the time. I mean, once the expression is generated, the CSE algorithm is able to reduce it significantly. So just to give you an example, if you generate a very large expression in SymPy, and then say, okay, well, I want to inject quantities, like numerical quantities, floating point quantities, into all the free variables. If you just tell SymPy, okay, substitute those in, and then give me the numerical output, it will take a lot longer for it to do that than if you first ran it through CSE first, and then did the substitution. I think there's one has to be careful once, yeah, go ahead.
It could be that there was a generation step that we didn't really try to debug which exact lines of code were slowing it down. But we did, when we introduced the scalar temp and as a way of doing it, it flows through, as I said, in 27 seconds. So in any event, it's a capability that you have to. It's another capability that you have for breaking down your equations. For should you need them, should you need it. I don't know where I don't know where the slowdown exactly came from, but I know that once you got the, sufficiently large number of complex expressions in one loop body, it was unable to do it.
Yeah, I mean, I'd like to look into that at some point. But yeah, thanks for letting me know about that. It's interesting.
So anyway, I think that covers the basic features which I have used and I have introduced to NRPy and features of NRPy I've exploited to get to where we want to go. And I think that in the end, that when this is done, when all the dust clears, I hope that this will be kind of like Paul Walker's original vision, where you can just type in your mathematical expressions and then you get a code that runs on a distributed system and is optimized for GPUs, even though GPUs didn't exist at the time he had that vision. So. The end.